Welcome to Tech with Kaushik. This is set 1 of our DOP-C02 and AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 1. Next, question number 1. This one focuses on CloudWatch metric filters. Scenario: a company operates a microservices architecture hosted on AWS Lambda behind an Amazon API gateway. The company releases new versions of a specific Lambda function frequently and tests them concurrently with a subset of production traffic. The client application version is passed in a custom HTTP header named xClient version during each API request. Following a recent release, users are reporting intermittent errors. A DevOps engineer needs to create custom Amazon CloudWatch metrics to track the number of requests by API endpoint, client version, and HTTP response code. The engineer has updated the Lambda function to log a structured JSON payload containing the endpoint name, client version, and response code for every execution. Which combination of steps is the most operationally efficient way to fulfill these metric requirements? Option A. Direct the Lambda function logs to an Amazon CloudWatch logs log group. Create a CloudWatch logs metric filter that publishes a request count metric from the structured JSON logs. Use endpoint name, client version, and HTTP response code as the 3 metric dimensions. Option B. Direct the Lambda function logs to an Amazon CloudWatch logs log group. Set up an Amazon event bridge rule to trigger on log group creation and execute an AWS step function state machine to parse the log lines and publish metrics. Option C. Enable API gateway execution logging to an Amazon S3 bucket. Configure an AWS Lambda function triggered by S3 object-created events to parse the logs, and use the putMetricData API to publish the metrics to CloudWatch with dimensions. Option D. Instrument the Lambda function with the AWS X-Ray SDK. Create an X-Ray subsegment capturing the endpoint name, response code, and client version. Use X-Ray Trace Analytics to automatically emit the aggregated metrics to CloudWatch. Go with Option A. Direct the Lambda function logs to an Amazon CloudWatch logs log group. Create a CloudWatch logs metric filter that publishes a request count metric from the structured JSON logs. Use endpoint name, client version, and HTTP response code as the 3 metric dimensions. This works because CloudWatch logs metric filters can transform structured JSON log events into custom metrics and can publish up to 3 dimensions. Using endpoint, client version, and response code as dimensions on one request count metric satisfies all 3 slicing requirements without custom metric publishing code. The other choices do not work because B. An event bridge rule on log group creation does not process each log event, and step functions adds unnecessary orchestration. C. S3 plus Lambda and putMetricData requires custom parsing and publishing. D. X-Ray provides tracing, but it does not automatically create the required 3-dimensional request count metric from these fields. The main takeaway is for structured CloudWatch logs, a metric filter can publish a custom metric with up to 3 dimensions. Use dimensions for the fields you need to slice. Question number 2. Let's go. A DevOps team maintains a serverless application consisting of an Amazon API Gateway REST API that invokes an AWS Lambda function. The Lambda function initializes by downloading a large machine learning model from Amazon S3 into memory, which causes a cold start duration of up to 10 seconds. The application experiences highly variable traffic. At noon, the traffic spikes to 15 times its baseline volume, and by midnight, it drops to 5% of its baseline. Customers report unacceptable latency when using the application intermittently throughout the day and during the rapid scaling period at noon. Which solution will minimize the Lambda function latency across all traffic patterns with the least operational overhead? Choices. Option A. Allocate reserved concurrency for the Lambda function with a baseline value. Configure a scheduled scaling policy on the API gateway to increase the limit before the noon spike. Option B. Enable provision concurrency on the Lambda function alias. Register the alias with application autoscaling. Use a scheduled action to raise the minimum provisioned concurrency before the recurring noon spike and a target tracking policy to adjust capacity with utilization outside the peak. Option C. Modify the Lambda function to download the machine learning model directly to an Amazon Elastic file system, Amazon EFS, volume to reduce the cold start time to under 1 second. Option D. Configure reserved concurrency on the Lambda function. Set the concurrency limit to the maximum expected concurrent executions during the noon spike. The answer here is option B. Enable provision concurrency on the Lambda function alias. Register the alias with application autoscaling. Use a scheduled action to raise the minimum provisioned concurrency before the recurring noon spike and a target tracking policy to adjust capacity with utilization outside the peak. Let's look at the reasoning. Provisioned concurrency pre-initializes Lambda execution environments. Application autoscaling supports both scheduled scaling and target tracking for provisioned concurrency. The scheduled action prepares capacity before the predictable noon surge, while target tracking adapts to variable traffic during the rest of the day with little custom automation. Now let's rule out the other options. A. Reserved concurrency limits or reserves concurrency but does not pre-initialize execution environments. An API gateway is not the scalable target for Lambda concurrency. C. EFS can change model loading behavior but does not guarantee removal of initialization latency. D. A static reserve concurrency ceiling does not eliminate cold starts and waste capacity planning effort. Keep this point in mind for the exam. For predictable Lambda spikes, combine scheduled scaling of provisioned concurrency with target tracking. Reserve concurrency alone does not remove cold starts. Question number 3. Scenario. A financial services company uses customer-managed AWS KMS keys. To meet strict regulatory compliance, the company requires on-demand manual key rotation and dictates that no KMS key can remain unrotated for more than 90 days. The security team also requires each violation to be recorded as a WS config noncompliance for audit history, with an automated notification when a key exceeds the limit. Which solution will meet this requirement with the least management overhead? Options. Option A. Enable an AWS config managed rule to check for KMS key rotation. Configure a remediation action using AWS Systems Manager to publish a message to an Amazon SNS topic. Option B. Create an Amazon Event Bridge rule scheduled to run daily. The rule must invoke an AWS Lambda function that iterates through all KMS keys, checks their last rotation date, and publishes to an Amazon SNS topic if the key is older than 90 days. Option C. Deploy a periodic AWS config custom rule backed by an AWS Lambda function. Have the function use AWS KMS rotation history to determine the date of the latest completed on-demand rotation and report noncompliance when the age exceeds 90 days. Route AWS config compliance change events through Amazon Event Bridge to an Amazon SNS topic. Option D. Configure AWS CloudTrail to monitor KMS, rotate key events. Use Amazon Event Bridge to trigger an Amazon SNS topic notification if no KMS, rotate key event is detected for a specific key within 90 days. In this case, choose option C. Deploy a periodic AWS config custom rule backed by an AWS Lambda function. Have the function use AWS KMS rotation history to determine the date of the latest completed on-demand rotation and report noncompliance when the age exceeds 90 days. Route AWS config compliance change events through Amazon Event Bridge to an Amazon SNS topic. The main reason is a periodic AWS config custom Lambda rule can evaluate a compliance requirement that is not covered by a suitable managed rule while preserving compliance history. The function can use AWS KMS rotation history data to identify the latest completed on-demand rotation. Event Bridge can then route config compliance changes to SNS. Here's why the alternatives are not suitable. Next, question number 4. This is a harder question, so check every requirement carefully. A DevOps team is setting up an AWS Control Tower landing zone for a large enterprise. The team is using AWS IAM Identity Center, AWS single sign-on, connected to an external identity provider, IDP, via SAML 2.0. The security team requires a robust, scalable permission model enforcing least privilege through attribute-based access control, ABAC. Developers must only be permitted to manage resources that belong to their specific project team. Which combination of steps is required to implement this ABAC model? Choose 3. Identify all valid responses. Options. Option A. Enable attributes for access control in IAM Identity Center. Map the required attributes from the external IDP as key value pairs. Option B. Create IAM permission sets in IAM Identity Center. Attach inline policies to the permission sets using the AWS principal tag condition key to scope access based on the attributes. Option C. Create a group in the external IDP and place the developers in the group. Assign this group to the corresponding AWS accounts and permission sets within IAM Identity Center. Option D. Create an AWS Lambda function to synchronize user tags from the external IDP directly into AWS IAM user objects on an hourly schedule. Option E. Enable attributes for access control in IAM Identity Center. Create a mapping rule that assigns local IAM tags to the users based on the mapped IDP groups. Option F. Apply AWS Resource Access Manager, AWS RAM, policies to automatically tag newly created resources with the AWS principal tag variables. The required selections are Option A. Enable attributes for access control in IAM Identity Center. Map the required attributes from the external IDP as key value pairs. Option B. Create IAM permission sets in IAM Identity Center. Attach inline policies to the permission sets using the AWS principal tag condition key to scope access based on the attributes. And Option C. Create a group in the external IDP and place the developers in the group. Assign this group to the corresponding AWS accounts and permission sets within IAM Identity Center. This is the best choice because to implement attribute-based access control, ABAC, using an external IDP with IAM Identity Center, you must enable attributes for access control in Identity Center and map the incoming IDP attributes to AWS tags. A. You define the permissions boundary and dynamic access and permission sets by using the AWS principal tag / key condition in IAM policies. B. Access assignment is handled by assigning the synchronized IDP groups to specific AWS accounts and the ABAC-enabled permission sets. C. The remaining options can be eliminated because D. You do not need a custom Lambda function to sync tags. IAM Identity Center maps attributes natively from the IDP SAML assertions or skim provisioning. E. Mapping rules are configured directly from the IDP attributes, not by assigning local IAM tags to the users based on groups. F. AWS RAM is used to share resources across accounts, like subnets or transit gateways, not for assigning or inheriting tags based on IAM principles. A helpful shortcut is this. When using ABAC with IAM Identity Center, pass user attributes from the IDP, map them in Identity Center, and reference them in permission set IAM policies using AWS principal tag. Question number 5. Let's go. Scenario. A DevOps engineer is updating an AWS CloudFormation template that deploys an internet-facing microservice. The service runs on Amazon EC2 instances located in a private subnet, scaled by an auto-scaling group behind an application load balancer, ALB. The company has mandated that the web service must accept incoming requests from external clients using IP version 6 addresses. How should the DevOps engineer modify the CloudFormation template to fulfill this requirement? Option A. Associate an IP version 6 CIDR block with the VPC and the public subnets that host the ALB. Add an IP version 6 default route :0 from those public subnets to the existing internet gateway. Allow the required IP version 6 client range on the ALB security group. Set the ALB IP address type to dual stack and keep the target group on IP version 4. Option B. Replace the ALB with a network load balancer, NLB. Attach an IP version 6 elastic IP address to the NLB. Route the IP version 6 traffic to the private subnets. Option C. Add an IP version 6 CIDR block to the VPC and the private subnets where the EC2 instances reside. Assign IP version 6 addresses to each EC2 instance and update the ALB target group to route directly to the instance's IP version 6 addresses. Option D. Assign an IP version 6 elastic IP address to each EC2 instance in the private subnet. Create a dual stack target group, add the instances, and attach the target group to the ALB. The right response is option A. Associate an IP version 6 CIDR block with the VPC and the public subnets that host the ALB. Add an IP version 6 default route :0 from those public subnets to the existing Internet gateway. Allow the required IP version 6 client range on the ALB security group. Set the ALB IP address type to dual stack, and keep the target group on IP version 4. An internet-facing ALB in dual stack mode can accept IP version 4 and IP version 6 clients while forwarding to an IP version 4 target group. The ALB subnets need IP version 6 address space and an IP version 6 route to the Internet gateway, and the ALB security group must allow the intended IP version 6 ingress. The private EC2 targets do not need IP version 6 solely for this requirement. B. Replacing the ALB with an NLB is unnecessary, and IP version 6 elastic IP addresses are not used this way. C. The backend instances do not need IP version 6 merely because clients use IP version 6. The dual stack ALB can forward to IP version 4 targets. D. Assigning public IP version 6 addressing to private backend instances bypasses the intended ALB architecture and is unnecessary. Here's a useful exam tip. For IP version 6 clients with IP version 4 backends, use a dual stack ALB, IP version 6 enable public ALB subnets, IP version 6 routing and security group rules. Targets may stay IP version 4. Now for question number 6. An enterprise uses AWS organizations and AWS Control Tower to govern a multi-account environment. The organization is subscribed to the AWS Enterprise Support Plan. A DevOps team provisions new accounts using Account Factory for Terraform, AFT. After provisioning, the team observes that the newly created AWS accounts are defaulting to the basic support plan instead of the enterprise support plan. The team needs to ensure all new accounts provisioned via AFT are automatically enrolled in the enterprise support plan. Which action will meet this requirement most efficiently? Here are the options. Option A. Implement an AWS config conformance pack across the organization to detect the support plan level and trigger an AWS Systems Manager automation runbook to upgrade the plan. Option B. Create an Amazon Event Bridge rule that reacts to new account creation events and invokes an AWS Lambda function with the support resolve case permission to open a support ticket. Option C. Update the AFT deployment configuration inputs by setting the aft_feature_enterprise_support feature flag to true and redeploy the AFT pipeline. Option D. Modify the AWS Control Tower landing zone parameters to include the AWS Enterprise Support variable, pointing to the management account ID. The best choice is option C. Update the AFT deployment configuration inputs by setting the aft_feature_enterprise_support feature flag to true and redeploy the AFT pipeline. Here's why. Account Factory for Terraform, AFT, includes built-in feature flags to handle common account baseline requirements. Setting the aft_feature_enterprise_support parameter to true in the AFT deployment configuration automatically manages the enrollment of newly provisioned accounts into the enterprise support plan by creating the necessary support cases under the hood. Let's quickly check the incorrect choices. A. While AWS config and SSM could technically automate this, AFT natively supports this feature, making custom automation unnecessary operational overhead. B. Event Bridge and Lambda require custom code maintenance and IAM role management, increasing overhead compared to toggling the native AFT feature flag. D. There is no native AWS Enterprise Support parameter directly in the AWS Control Tower landing zone parameters. This is an AFT-specific feature flag. When using Account Factory for Terraform, AFT, rely on its native feature flags, like aft_feature_enterprise_support, aft_feature_cloudtrail_events, etc., to minimize custom automation overhead. Here comes question number 7. This question takes us into event-driven automation. Consider this situation. A company manages a large fleet of Amazon EC2 instances. Occasionally, a AWS Health dashboard issues notifications indicating that specific EC2 instances require a restart due to underlying hardware maintenance. The company uses AWS Systems Manager maintenance windows to perform disruptive actions to minimize business impact. A DevOps engineer must automate the process of rebooting these affected EC2 instances exclusively during their designated maintenance windows. Which solution will achieve this requirement? Choice A. Create an Amazon Event Bridge rule matching AWS health events for EC2 instance maintenance. Set the target to an AWS Systems Manager automation document that immediately restarts the affected instance. Choice B. Create an Amazon Event Bridge rule matching AWS health events for EC2 instance maintenance. Set the target to an AWS Lambda function that registers an automated task to restart the instance in the upcoming Systems Manager maintenance window. Choice C. Create an Amazon Event Bridge rule matching AWS Systems Manager maintenance window execution events. Set the target to an AWS Lambda function that queries AWS health and restarts any flagged instances. Choice D. Configure AWS config with a managed rule checking for pending EC2 maintenance. Use an auto-remediation action targeting a Systems Manager document to schedule the restart during the next maintenance window. In this case, choose option B. Create an Amazon Event Bridge rule matching AWS health events for EC2 instance maintenance. Set the target to an AWS Lambda function that registers an automated task to restart the instance in the upcoming Systems Manager maintenance window. This works because AWS Health Dashboard publishes events to Event Bridge when an EC2 instance requires maintenance. Because the requirement explicitly states the restart must happen during their designated maintenance windows, you cannot trigger an immediate restart. Instead, you capture the Event Bridge event and trigger a Lambda function that schedules the specific EC2 instance to be rebooted during its predefined AWS Systems Manager maintenance window. The other choices do not work because A. Targeting the Systems Manager automation document directly from the Event Bridge rule would immediately restart the EC2 instance, violating the requirement to perform the action during the maintenance window. C. Systems Manager maintenance window execution events occur when the window opens. By then, it is too late or requires complex logic to query AWS health in real time. The best practice is to schedule the task as soon as the health event is received. D. AWS config does not natively manage scheduling actions for future maintenance windows via auto-remediation. Auto-remediation is designed to execute as soon as the non-compliant state is detected. The main takeaway is for delayed remediation actions, like waiting for a maintenance window. Capture the event dynamically with Event Bridge and use a Lambda function to register the task into the future maintenance window schedule. Next up is question number 8. Here's the scenario. A DevOps team provides reusable AWS CloudFormation templates to application developers. One template provisions an Amazon EC2 instance that runs a data processing application, alongside an Amazon S3 bucket used for temporary object storage. When developers delete the CloudFormation stack, the process occasionally fails, leaving the S3 bucket and the stack in a delete_failed state. The S3 bucket is not configured with versioning. The team needs to ensure the stack can be cleanly deleted without manual intervention. What is the most operationally efficient solution to resolve this error? The choices are: Choice A. Add the deletion policy. Delete attribute to the S3 bucket resource definition in the CloudFormation template to force deletion. Choice B. Add a custom resource to the template backed by an AWS Lambda function. Configure the custom resource to empty the S3 bucket when it receives a delete request type during stack deletion. Choice C. Switch the deployment framework from AWS CloudFormation to AWS Elastic Beanstalk to natively handle the lifecycle of the S3 bucket and EC2 instance. Choice D. Configure an S3 lifecycle rule on the bucket to expire all objects after 1 day. Wait 24 hours before attempting to delete the CloudFormation stack. Go with option B. Add a custom resource to the template backed by an AWS Lambda function. Configure the custom resource to empty the S3 bucket when it receives a delete request type during stack deletion. Let's look at the reasoning. AWS CloudFormation cannot delete an Amazon S3 bucket if it contains objects. To automate the deletion of a populated S3 bucket when a stack is deleted, a CloudFormation custom resource backed by an AWS Lambda function is required. The Lambda function will receive a delete event from CloudFormation, iteratively delete all objects in the S3 bucket, and signal success back to CloudFormation, allowing the stack deletion to proceed. Now let's rule out the other options. A. The deletion policy. Delete attribute is the default behavior for S3 buckets, but it will still fail if the bucket is not empty. C. Switching to Elastic Beanstalk is a massive architectural change that does not directly solve the underlying S3 bucket constraint. S3 lifecycle rules are evaluated asynchronously, usually once a day, and cannot guarantee the bucket will be immediately empty when the developer clicks delete on the CloudFormation stack. Keep this point in mind for the exam. CloudFormation will not delete an S3 bucket that contains objects. The standard operational workaround is to use a Lambda-backed custom resource to empty the bucket during the stack delete event. Question number 9. The focus now shifts to CI/CD pipelines. A DevOps engineer maintains an AWS code pipeline in the EU Central 1 region. The pipeline compiles application code using an AWS code build action and deploys it via an AWS CloudFormation deploy action to the same region. The business now requires the application to also be deployed to the West 2 region as part of the same pipeline. The DevOps engineer has updated the code build spec file to generate an additional deployment artifact specifically packaged for West 2. Which combination of steps must the DevOps engineer take to successfully deploy the application to the West 2 region using the existing pipeline in EU Central 1? Choose 2. More than one answer may be correct. Choices. Option A. Create a new AWS CloudFormation deploy action in the pipeline targeting West 2, configuring it to use the new output artifact generated by code build. Option B. Modify the AWS CloudFormation template to include an AWS Systems Manager parameter store lookup for the region-specific deployment package. Option C. Add an Amazon S3 bucket in West 2 to act as an artifact store. Update the pipeline configuration to define artifact stores containing mappings for both EU Central 1 and West 2. Option D. Create an Amazon S3 bucket in West 2. Configure S3 cross-region replication, CRR, to replicate the output artifacts from the EU Central 1 pipeline bucket to West 2. E. Configure a new AWS code deploy application in West 2 and add it as a deployment provider stage in the pipeline. The correct answers are Option A. Create a new AWS CloudFormation deploy action in the pipeline targeting West 2, configuring it to use the new output artifact generated by code build, and Option C. Add an Amazon S3 bucket in West 2 to act as an artifact store. Update the pipeline configuration to define artifact stores containing mappings for both EU Central 1 and West 2. The main reason is to support cross-region actions in AWS code pipeline. You must provide an artifact bucket in every region where actions execute. The pipeline configuration must be updated to use the artifact stores map instead of a single artifact store, specifying the S3 bucket for West 2C. Code pipeline handles the cross-region replication of artifacts automatically. You then add the CloudFormation deploy action for West 2 using the artifact produced by code build. A. Here's why the alternatives are not suitable. B. Using parameter store lookups in the CFN template is unnecessarily complex when code pipeline natively passes artifacts to CloudFormation deploy actions. D. Setting up custom S3 cross-region replication, CRR, is not required. AWS code pipeline automatically copies artifacts between regional artifact stores if configured correctly via the artifact stores parameter. E. The scenario states the application is deployed via AWS CloudFormation. Adding AWS code deploy introduces a different deployment engine entirely. Exam tip. Cross-region code pipeline deployments require an S3 artifact bucket in each target region. You configure this using the artifact stores mapping in the pipeline definition, and code pipeline automatically handles copying the artifacts between regions. Question number 10. Let's go. An enterprise uses AWS organizations to manage multiple AWS accounts. The security team mandates that Amazon S3 block public access must remain enabled at the bucket level across all accounts. If AWS config detects any bucket as non-compliant, the security team must receive a notification through Amazon SNS with minimal delay. A DevOps engineer must implement this solution centrally. Individual member accounts must not be able to modify, turn off, or bypass the centrally deployed compliance rule or its remediation configuration. Which solution meets these requirements with the highest level of enforcement? Choices. Option A. Enable Amazon Guard duty across the organization using a delegated administrator account. Create an Amazon Event Bridge rule in the administrator account that captures S3 block public access findings and routes them to an SNS topic. Option B. Use AWS Cloud Formation stack sets from the management account to deploy an Amazon Event Bridge rule to all member accounts. Configure the rule to match CloudTrail S3. Put bucket public access block events and target a central SNS topic. Option C. Enable AWS config across the organization. From the management account or a delegated administrator, deploy an organization conformance pack containing the S3 bucket level public access prohibited managed rule and an AWS Systems Manager automation remediation action that publishes to the central SNS topic. Option D. Enable AWS CloudTrail organizational trails. Configure an AWS Lambda function in the central logging account to parse the logs continuously for S3. Put bucket public access block calls and publish alerts to an SNS topic. The answer here is option C. Enable AWS config across the organization. From the management account or a delegated administrator, deploy an organization conformance pack containing the S3 bucket level public access prohibited managed rule and an AWS Systems Manager automation remediation action that publishes to the central SNS topic. This is the best choice because AWS config organization conformance packs centrally deploy config rules and remediation actions across member accounts. AWS documents that the underlying organization-managed rules and remediation actions are not modifiable by member accounts. The S3 managed rule detects non-compliant bucket public access settings, and Systems Manager automation can publish the notification to SNS. The remaining options can be eliminated because A. Guard duty is a threat detection service and is not the authoritative control for this configuration compliance state. B. Stack sets can deploy event bridge rules, but member account administrators could alter those rules unless additional preventive controls are added. D. Central CloudTrail parsing is custom detection and does not provide the same organization-managed config compliance control. A helpful shortcut is this. Use AWS config organization rules or conformance packs when compliance controls must be centrally managed and resistant to modification by member accounts. Next, question number 11. Scenario. A DevOps engineer maintains an automated image building pipeline in a source AWS account. The pipeline generates an unencrypted Amazon machine image, AMI. The engineer needs to share this AMI with a separate target AWS account, where an Amazon EC2 auto-scaling group will use it to launch instances. Company policy requires that all AMIs shared across accounts must be encrypted. The engineer has already created a customer-managed AWS key management service, AWS KMS, key in the source account. Which combination of steps must the DevOps engineer perform to ensure the auto-scaling group in the target account can successfully launch instances from the encrypted AMI? Choose 4. Select all answers that apply. Options. Option A. In the source account, copy the unencrypted AMI to create a new encrypted AMI using the newly created customer-managed KMS key. Option B. In the source account, copy the unencrypted AMI to create a new encrypted AMI using the default AWS managed EBS encryption key, AWS/EBS. Option C. In the source account, update the KMS key policy to grant the target account permissions to use the key and create grants. Option D. In the target account, create a KMS grant that delegates decryption permissions to the auto-scaling group's service-linked role. Option E. In the source account, share the unencrypted AMI directly with the target account and enforce encryption during the instance launch. Option F. In the source account, explicitly share the newly encrypted AMI with the target account. You should choose option A. In the source account, copy the unencrypted AMI to create a new encrypted AMI using the newly created customer-managed KMS key. Option C. In the source account, update the KMS key policy to grant the target account permissions to use the key and create grants. Option D. In the target account, create a KMS grant that delegates decryption permissions to the auto-scaling group's service-linked role. And option F. In the source account, explicitly share the newly encrypted AMI with the target account. A creates an AMI whose snapshots use a shareable customer-managed KMS key. C authorizes the target account to use the source key and create grants. F gives the target account launch permission for the encrypted AMI. D grants the target account's auto-scaling service-linked role the KMS permissions it needs when launching encrypted volumes. B. An AMI backed by snapshots encrypted with the default AWS-managed EBS key cannot be shared across accounts. E. Sharing the unencrypted AMI violates the stated policy and does not establish the required encrypted cross-account artifact. Here's a useful exam tip. Cross-account encrypted AMI use requires 4 pieces: customer-managed key encryption, AMI sharing, cross-account KMS key authorization, and KMS access for the target auto-scaling service-linked role. Question number 12. We're moving on to security automation. Here's what is happening. An enterprise maintains hundreds of AWS accounts governed by AWS organizations. The central security policy mandates that all external application load balancers, ELBs, must be protected by an AWS WAF Web ACL. During a routine security audit using AWS Config, the security team discovers multiple recently provisioned ALBs across various accounts that are not associated with any AWS WAF Web ACL. A DevOps engineer is tasked with preventing this violation from occurring on newly created ELBs automatically in the future. Which combination of steps will accomplish this across the entire organization? Choose 2. Choose every option that satisfies the requirement. Review the options. Option A. Delegate an AWS Firewall Manager Administrator account within AWS organizations. Option B. Delegate an Amazon Guard Duty Administrator account within AWS organizations. Option C. Create an AWS Firewall Manager security policy configured to automatically attach the required AWS WAF Web ACL to any in-scope ALB. Option D. Create an AWS Config Conformance Pack with an automatic remediation document that destroys non-compliant ALBs. Option E. Set up an AWS Systems Manager State Manager Association across all accounts to install the AWS WAF agent on ALBs. The answers that work here are Option A. Delegate an AWS Firewall Manager Administrator account within AWS organizations, and Option C. Create an AWS Firewall Manager security policy configured to automatically attach the required AWS WAF Web ACL to any in-scope ALB. Here's why. AWS Firewall Manager is specifically designed to centrally manage and enforce security rules across accounts in AWS organizations. By delegating a security account as the Firewall Manager Administrator, A. The security team can create a single security policy that automatically detects newly created ALBs and API gateways and attaches the required AWS WAF Web ACLs to them automatically. C. Let's quickly check the incorrect choices. B. Amazon Guard Duty is a threat detection service, not a centralized firewall enforcement tool. D. While AWS Config can detect violations, Firewall Manager is the native, purpose-built service for managing and enforcing WAF Web ACLs at scale across an organization without requiring custom SSM remediation documents. E. AWS WAF is attached to resources via API integration. There is no WAF agent to install on an ALB. Use AWS Firewall Manager to centrally enforce and automatically deploy AWS WAF Web ACLs, AWS Shield Advanced Protections, and VPC security groups across an entire AWS organization. Question number 13. Scenario. A company mandates that every Amazon Elastic Block Store, Amazon EBS, volume must be tagged with a key named backup tier to determine its backup schedule. Valid values are none, standard, or premium. This requirement applies even if a volume does not require a backup. A recent audit showed that developers occasionally forget to add the backup tier tag when provisioning new EBS volumes. A DevOps engineer must implement a solution that continuously audits tag compliance and automatically applies a backup tier tag with a default value of standard if the tag is missing. Which solution will meet this requirement with the least administrative overhead? Option A. Configure an AWS CloudTrail trail to log API events. Create an Amazon Event Bridge rule filtering for create volume events. Route the event to an AWS Lambda function that applies the missing tag. Option B. Deploy the AWS config managed rule required tags specifying backup tier as the required tag key. Configure a custom AWS Systems Manager automation document as the auto-remediation action to add backup tier equals standard when the tag is missing. Option C. Enable AWS Cloud Trail logging. Create an Amazon Event Bridge rule that reacts to modify volume events. Use an AWS Systems Manager run command target to apply the missing tag to the EC2 instances. Option D. Create a custom AWS config rule backed by an AWS Lambda function to evaluate compliance of EC2 instance tags. Configure a remediation action to apply the backup tier tag to all non-compliant resources using the AWS CLI. The best choice is option B. Deploy the AWS config managed rule required tags specifying backup tier as the required tag key. Configure a custom AWS Systems Manager automation document as the auto-remediation action to add backup tier equals standard when the tag is missing. This works because the AWS config required tags managed rule supports EBS volumes and can detect a missing backup tier tag. AWS config can invoke a custom Systems Manager automation runbook for remediation. The runbook can call the tagging API to add backup tier equals standard only when the tag is absent, providing continuous detection and automatic correction without a custom config rule. The other choices do not work because A. Event Bridge plus Lambda handles new create volume events but requires custom code and does not naturally audit existing volumes. C. Run command changes an operating system, not EBS control plane tags. D. A custom config Lambda rule is unnecessary because required tags already evaluates EBS tags. The main takeaway is AWS documents that AWS set required tags does not work as remediation for required tags. Use the managed config rule with a custom Systems Manager automation runbook. Question number 14. A security team uses a centralized auditing application hosted in an isolated AWS account. This application assumes a specific cross-account IAM role named Security Audit Role provisioned in every member account within an AWS organization. Recently, a developer with administrative access in one of the member accounts accidentally modified the trust policy of the security audit role, breaking the auditing application's access. The DevOps team must ensure that no entity within any member account can modify or delete the security audit role, except for the organization's central security administrator role. Which configuration will enforce this requirement most effectively? Option A. Apply an IAM permissions boundary to the security audit role in all member accounts. Include a deny statement for all IAM modification actions, with a condition allowing the central security administrator role. Option B. Create an SCP that denies IAM actions that can modify or delete the security audit role, including IAM. Update assume role policy, IAM. Update role, IAM. Delete role, IAM. Put role policy, IAM. Delete role policy, IAM. Attach role policy, and IAM. Detach role policy. On the security audit role, ARN. Use an ARN condition on AWS. Principal ARN to exempt only the central security administrator role and attach the SCP to the organization root. Option C. Create an AWS Cloud Trail rule detecting modifications to the security audit role. Trigger an AWS Lambda function to revert the changes and notify the security team. Option D. Deploy an AWS config custom rule that continually checks the IAM policies attached to the security audit role. Configure an automated remediation action to revert any unauthorized modifications. The right response is option B. Create an SCP that denies IAM actions that can modify or delete the security audit role, including IAM. Update assume role policy, IAM. Update role, IAM. Delete role, IAM. Put role policy, IAM. Delete role policy, IAM. Attach role policy, and IAM. Detach role policy. On the security audit role, ARN. Use an ARN condition on AWS. Principal ARN to exempt only the central security administrator role and attach the SCP to the organization root. Let's look at the reasoning. An SCP can impose an explicit deny across member accounts even when a local principal has administrator permissions. The deny must include IAM. Update assume role policy because that action changes a role trust policy, along with the other role policy mutation and deletion actions. An ARN condition on AWS. Principal ARN can exempt the authorized central administrator. Now let's rule out the other options. A. A permissions boundary limits permissions of the identity to which it is attached. It is not a tamper-resistant organization-wide guardrail against other administrators. C. CloudTrail plus Lambda reacts after a prohibited change. D. AWS config remediation is also detective/reactive rather than a preventive organization guardrail. Keep this point in mind for the exam. To protect a shared IAM role across member accounts, use an SCP explicit deny and include IAM. Update assume role policy when trust policy changes must be blocked. Question number 15. Consider this situation. A company runs microservices on Amazon Elastic Kubernetes Service, Amazon EKS. The DevOps team needs to establish an automated alerting mechanism that parses EKS control plane log events. Based on specific error codes found in the control plane logs, notifications must be routed via Amazon SNS to different operational teams. The team plans to use an AWS Lambda function to inspect the incoming log stream and selectively publish messages to the appropriate SNS topics. Which logging configuration will support this architecture efficiently? The choices are: Option A. Enable EKS control plane logging to Amazon S3. Configure an S3 event notification for S3, object created asterisk to trigger the Lambda function to download and parse the log files. Option B. Enable EKS control plane logging to Amazon CloudWatch logs. Create a CloudWatch log subscription filter specifying the Lambda function as the destination. Option C. Enable EKS control plane logging to Amazon CloudWatch logs. Create a scheduled Amazon Event Bridge rule that executes a CloudWatch logs insights query every minute and sends the results to the Lambda function. Option D. Install the Amazon CloudWatch agent inside the EKS cluster. Configure the agent to stream application logs directly to Amazon SNS using an IAM role. Go with option B. Enable EKS control plane logging to Amazon CloudWatch logs. Create a CloudWatch log subscription filter specifying the Lambda function as the destination. The main reason is Amazon EKS natively integrates with Amazon CloudWatch logs to capture control plane logs, such as API, audit, authenticator, controller manager, and scheduler logs. CloudWatch log subscription filters can evaluate incoming log events in real time, matching specific patterns like error codes. When a match occurs, the filter seamlessly streams the log data directly to an AWS Lambda function, which can execute custom logic to route notifications to the correct SNS topics. Here's why the alternatives are not suitable. A. Delivering EKS logs to S3 involves a delay. Log files are written periodically. This is not suited for real-time alerting. S3 events triggered on log file delivery also require complex logic to parse entire batch files rather than streaming individual log events. C. Polling CloudWatch logs insights via Event Bridge every minute is an inefficient anti-pattern compared to native, push-based subscription filters. D. The CloudWatch agent installed inside EKS collects worker node or application logs, not the AWS-managed EKS control plane logs. Exam tip. For near real-time processing or alerting based on log events generated in AWS, route the logs to CloudWatch logs and use a subscription filter targeting AWS Lambda or Amazon Kinesis. Question number 16. Let's go. A DevOps engineer is configuring observability for an application running on Amazon Elastic Container Service, Amazon ECS. The application is exposed to the internet through an application load balancer, ALB, routing traffic to ECS target groups. The engineer must collect both the application logs generated by the ECS tasks and the access logs from the ALB. All logs must be delivered to a central Amazon S3 bucket for near real-time ingestion by a third-party SIEM tool. Which combination of steps will meet these requirements? Choose 3. More than one answer may be correct. Choices. Option A. Enable access logging directly on the ALB and configure it to deliver logs to the target S3 bucket. Option B. Update the ECS task definitions to use the OSLogs log driver, routing the application logs to an Amazon CloudWatch logs log group. Option C. Configure an Amazon Kinesis data firehose delivery stream targeting the S3 bucket. Create an Amazon CloudWatch log subscription filter pointing the log group to the delivery stream. Option D. Enable access logging on the ECS target groups and configure them to push logs directly to the target S3 bucket. E. Install the CloudWatch agent on the ECS container instances and configure it to batch logs to an Amazon Event Bridge rule. F. Schedule an AWS Lambda function to run every minute using Amazon Event Bridge to execute the Create Export Task API, dumping the CloudWatch logs to the target S3 bucket. The correct answers are option A. Enable access logging directly on the ALB and configure it to deliver logs to the target S3 bucket. Option B. Update the ECS task definitions to use the oslogs log driver, routing the application logs to an Amazon CloudWatch logs log group. And option C. Configure an Amazon Kinesis data firehose delivery stream targeting the S3 bucket. Create an Amazon CloudWatch log subscription filter pointing the log group to the delivery stream. This is the best choice because ALB access logs can be natively configured to write directly to Amazon S3A. ECS Fargate and EC2 tasks natively support the oslogs log driver, which forwards stout/stare application logs to CloudWatch logs. B. To deliver logs from CloudWatch logs to S3 in near real time without writing custom code, you use an Amazon CloudWatch log subscription filter pointing to an Amazon Kinesis data firehose delivery stream configured with the S3 bucket destination. C. The remaining options can be eliminated because D. Target groups do not have their own access logging feature. Access logging is configured at the load balancer level. E. Installing the CloudWatch agent on ECS instances is an older pattern for EC2-backed ECS, but the oslogs driver is native, simpler, and works for both EC2 and Fargate. Furthermore, Event Bridge is not a log batching target. F. The Create Export Task API is intended for bulk, offline log exports and can take a long time to complete. It is not suitable for near real-time continuous ingestion. A helpful shortcut is this. Application load balancers natively log directly to S3. ECS application logs natively use the oslogs driver to reach CloudWatch logs. To move logs from CloudWatch logs to S3 in near real time, use Kinesis data firehose. Next, question number 17. Scenario. A data ingestion pipeline receives IoT sensor data through an Amazon API gateway, which places the raw data into an Amazon Simple Queue service, Amazon SQS, standard queue. A backend worker application pulls the queue, normalizes the data, and stores it in a database. Due to occasional malformed payloads from misconfigured sensors, the worker application occasionally crashes while parsing specific messages. Because the messages are not successfully processed, they reappear in the SQS queue and cause continuous parsing failures. A DevOps engineer needs to isolate these failing messages so developers can inspect and eventually reprocess them without blocking valid sensor data. Which solution will meet these requirements with the least application code change? Options. Option A. Create an AWS Lambda function triggered by Amazon Event Bridge to pull the SQS queue every minute. Inspect the sent timestamp of each message and delete messages older than 5 minutes. Option B. Modify the worker application to catch parsing exceptions. When an exception occurs, publish the problematic message directly to an Amazon SNS topic and remove it from the SQS queue. Option C. Create a new SQS queue to serve as a dead letter queue, DLQ. Configure a redrive policy on the primary SQS queue, setting the max receive count to a low threshold, for example, 3, and point it to the DLQ. Option D. Change the SQS queue to a FIFO queue. Use message deduplication IDs to automatically discard repeated messages if they fail processing more than once. In this case, choose option C. Create a new SQS queue to serve as a dead letter queue, DLQ. Configure a redrive policy on the primary SQS queue, setting the max receive count to a low threshold, for example, 3, and point it to the DLQ. A dead letter queue, DLQ, is a native SQS feature designed exactly for this scenario. If a consumer application fails to process a message successfully because of an exception, meaning it doesn't call delete message, the message reappears in the queue after the visibility timeout expires. By configuring a redrive policy, SQS will automatically move the message to the DLQ after it has been received and fail the specified number of times, max receive count. This isolates poison pill messages with 0 application code changes. A. Polling SQS via Lambda to check timestamps is an anti-pattern. SQS natively handles failing message routing via DLQs. B. Modifying the application to catch the error and send to SNS works, but requires custom code changes, whereas the DLQ feature handles this natively at the queue level. D. FIFO queues guarantee order and exactly once processing, but do not automatically isolate failing poison pill messages without a DLQ. Here's a useful exam tip. Whenever consumer applications repeatedly fail to process poison pill messages in Amazon SQS, the standard solution is to configure a dead letter queue, DLQ, using a redrive policy. Next, question number 18. Next, let's move into security auditing. Scenario. A company runs hundreds of Amazon EC2 instances across a multi-account AWS environment. Amazon Inspector is enabled through a delegated administrator. For this workload, the administrator has explicitly selected the agent-based EC2 scan mode so that only SSM-managed instances are scanned continuously. The affected instances are in private subnets with centralized egress connectivity to AWS service endpoints through a transit network. During a review, some EC2 instances appear as unmanaged or not scanning because they are not successfully managed by AWS Systems Manager. Which combination of actions will allow Amazon Inspector to successfully scan these instances? Choose 3. Identify all valid responses. Options. Option A. Ensure the AWS Systems Manager agent, SSM agent, is installed and actively running on the affected EC2 instances. Option B. Configure the security groups attached to the affected EC2 instances to allow outbound HTTPS, port 443, traffic to the Systems Manager service endpoints. Option C. Attach an IAM instance profile to the affected EC2 instances that includes the Amazon SSM Managed Instance Core Managed policy. Option D. Create an IAM role with the Inspector 2, start assessment run permission, and attach it to the Amazon Inspector Delegated Administrator account. E. Install the Amazon Inspector Classic agent on the instances using EC2 user data during launch. F. Configure the VPC route tables to allow inbound SSH, port 22, connections from the Amazon Inspector service IP ranges. You should choose option A. Ensure the AWS Systems Manager agent, SSM agent, is installed and actively running on the affected EC2 instances. Option B. Configure the security groups attached to the affected EC2 instances to allow outbound HTTPS, port 443, traffic to the Systems Manager service endpoints. And option C. Attach an IAM instance profile to the affected EC2 instances that includes the Amazon SSM Managed Instance Core Managed policy. Here's why. In agent-based EC2 scan mode, Amazon Inspector requires the instance to be managed by Systems Manager. That requires a running SSM agent. A. Network reachability to the required Systems Manager endpoints over HTTPS. B. And permissions for Systems Manager to manage the instance, commonly through an instance profile with Amazon SSM Managed Instance Core. C. Let's quickly check the incorrect choices. D. Inspector does not require a per-scan start assessment run role to make an EC2 instance SSM managed. E. Current Amazon Inspector EC2 scanning uses its current SSM-based /VM scanner mechanisms rather than the Amazon Inspector Classic agent. F. Agent-based scanning does not require inbound SSH from Inspector. First, identify the Inspector EC2 scan mode. Agent-based scanning requires SSM-managed instances. Hybrid mode can use agentless EBS snapshot scanning for eligible unmanaged instances. Next up is question number 19. A company uses AWS organizations to manage multiple AWS accounts. Currently, AWS config is configured manually in only a few accounts. The central security account is already registered as the delegated administrator for AWS config. The security and compliance team wants to centrally deploy AWS config recording to all current and future member accounts. They also need a centralized view to query resource configurations and track changes across the organization from that security account. Which combination of actions should a DevOps engineer perform to meet these requirements with the least management overhead? Choose 2. Choose every option that satisfies the requirement. Review the options. Choice A. Use AWS Cloud Formation Stack sets from the management account to deploy AWS config configuration recorders and delivery channels to all member accounts. Choice B. Register the central security account as a delegated administrator for AWS config in AWS organizations. Choice C. Create an AWS config organization aggregator in the delegated administrator account to collect data from all AWS accounts in the organization. Choice D. Create an Amazon EventBridge rule in the management account to capture resource changes and stream them via Amazon Kinesis to the security account. Choice E. Configure Amazon May-C in the delegated administrator account to automatically deploy AWS config recorders across the organization. The required selections are Option A. Use AWS Cloud Formation stack sets from the management account to deploy AWS config configuration recorders and delivery channels to all member accounts, and Option C. Create an AWS config organization aggregator in the delegated administrator account to collect data from all AWS accounts in the organization. This works because AWS config must first be enabled in the source accounts. Stack sets with service-managed permissions can deploy configuration recorders and delivery channels to current and future organization accounts. A. An organization configuration aggregator in the already registered delegated administrator account then collects recorded config data for centralized queries and compliance views. C. The other choices do not work because B. Delegated administrator registration is a prerequisite, but the scenario states it is already complete. Repeating it does not deploy recorders or create the aggregator. D. EventBridge and Kinesis duplicate AWS config's native aggregation function. E. May-C does not deploy AWS config recorders. The main takeaway is an AWS config aggregator only aggregates data that source accounts record. Enable config organization-wide, then aggregate it centrally from the management or delegated administrator account. Now for question number 20. Here's the scenario. A mission-critical application connects to an Amazon Aurora MySQL DB cluster. The database team has scheduled a mandatory engine version upgrade during a maintenance window. The source and target engine versions are supported by Amazon Aurora Blue/Green deployments. The DevOps engineer must minimize production disruption while allowing the upgraded environment to be validated before cutover. What is the most effective architectural change to minimize database downtime during the upgrade? Here are the options. Option A. Create an Amazon RDS Blue/Green deployment for the Aurora cluster. Upgrade the engine version in the green environment, validate the green environment, and switch over during the maintenance window. Option B. Take a manual snapshot of the Aurora cluster. Spin up a secondary cluster from the snapshot and switch the application traffic to the new cluster using Amazon Route 53 weighted routing. Option C. Enable Aurora Global Database and add a secondary region. Promote the secondary region to primary during the maintenance window and fail back afterward. Option D. Create a custom any endpoint containing the primary instance. Direct all application traffic to the custom endpoint. The best choice is Option A. Create an Amazon RDS Blue/Green deployment for the Aurora cluster. Upgrade the engine version in the green environment. Validate the green environment, and switch over during the maintenance window. Let's look at the reasoning. Aurora Blue/Green deployments are purpose-built to reduce risk and downtime for database updates, including supported major or minor engine upgrades. They create a synchronized green staging environment where the upgrade can be validated before an RDS-managed switchover redirects production to the green cluster with short, predictable disruption. Now let's rule out the other options. B. Snapshot Restore creates a point-in-time copy and requires custom synchronization and traffic cutover. C. Aurora Global Database is primarily a multi-region resilience architecture and is unnecessary for a planned local engine upgrade. D. A custom endpoint does not create an independently upgraded staging environment or orchestrate an upgrade switchover. Keep this point in mind for the exam. For supported Aurora engine upgrades that need validation and minimal cutover downtime, prefer RDS Blue/Green deployments over replica-only or snapshot-based workarounds. You have completed Set 1 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.